If you count their last playoff run they had, that was out of nowhere after like another decade of being shitty.
Yeah. I haven't watched any hockey this year. I don't have a good way to watch.
Yeah.
They
NHL subscription is the best way in my opinion. And then you just use a VPN to get local games, to block out local games, which is so dumb because Rogers owns the rights to the NHL streaming thing, and Sportsnet local games is Rogers Sportsnet. So they literally block their own network for local rights. Like, I even emailed them, I was like, on Twitter or whatever, like, so you guys realize you're blocking your own content, right? Like, it makes no sense. I pay for Rogers Sportsnet through TELUS, I pay for NHL.com, but I can't watch this fucking Oilers game right now.
Yeah, it's kind of weird that they do.
we just want your money. We're not giving you any service.
Yeah, exactly. I mean, the way the league's split up this year, like, there shouldn't be geographical restrictions, like, it makes no sense.
All right. Let me see. Sorry about the delay. We'll get going with this. So, service feeders and branch circuits. We did this for houses. We'll take through this fairly quick. Take away some of that glare. When it comes to apartments, thanks. Yeah, that shows up better there too. When it comes to apartments, there's two things we gotta take care of. First off, of course, there's the actual apartments, right, where the people are living, right, the dwelling units within the apartment, which are calculated based on 8202 sub rule 1. And like I said, when we went through this on Wednesday, pretty much the same as a house, only the watts per square meter is a little different. In that same process, right? You typically aren't going to have water heaters and stuff like that within the apartments. Generally, those are fed out of a house panel, where because they're central to everywhere, and that's where kind of the difference comes in. So, in an apartment, you always got your hallways. Quite often, common laundry facilities. You might have if it's a nice apartment, you might have a pool, whatever. So when we talk about house panel loads, that's all that stuff that's outside of the dwelling units. Okay, so it's just a terminology thing for this point, because you'll see house panel referred to quite a bit. Now, all those loads that are outside of the dwelling units, when we calculate them all up, we add them at a rate of 75% to our main service, and that's because again, not everything's used at always at the same time, but we got to allow quite a bit of that load. So what we do when we do an apartment building is you figure out your demand based on the dwelling units, and then you determine everything that's located outside of the dwelling units, everything that's common, and then add that to your main service at 75%, and that's how you determine your full apartment main service capacity. Air conditioning, electric heating, electrical vehicle chargers, and parking lots all have their own special demand, and so we still treat those a little bit differently. Electric heating, what catches a lot of people with electric heating is when we did it when we looked at it when we were doing single dwelling calculations, right? If you read 62.118, it talks about electric space heating with individual thermostats located within dwelling units. And you took the first 10 kilowatts at 100%, and everything above the 10 kilowatts at 75%. When you have electric heating in apartment buildings, you really got to watch, because quite often it's for entry vestibules. You might have heaters running underneath the sidewalks and that to keep the ice from building up, things like that. Those aren't heating loads with individual thermostats in dwelling units, right? So when we look at electric heating in an apartment building, you have to kind of take the stuff that's located in the apartments, treat it one way, and then all the electric heating that's outside the individual apartments and treat it its own way. Basically, it just means added at 100%. Car receptacles. If you have a look in your code book, Rule 8400, if you're doing a parkade, outdoor parkade or whatever, where you've got plugs for block heaters, we have a specific demand for those based on the ampacity of the circuits that are feeding the plugs. Okay, you'll see there's two tables there on page 103. There's one for parking plugs on a 15 amp circuit, another one on another column for plugs on a 20 amp circuit. You'll also see that there is a difference between controlled or restricted parking plugs and standard. Okay, controlled or restricted parking lot plugs. This is done in fairly large facilities to kind of limit the amount of energy being used by those block heater plugs. For example, the system here at the college, the outdoor parking pedestals, power pedestals, they're on a 20-minute on, 20-minute off cycle, and broke into 3 different quadrants. So this parking lot out here will be on for 20 minutes, and it shuts off for 40. When it shuts off, the one out behind comes on for 20 minutes, and it shuts off, and it's off for 40. And when it shuts off, the one over by the administration, on the other side of the administration building, it comes on for 20 minutes, shuts off, and then goes through the cycle again, right? So it allows full current, but only a third of the time, and that way they reduce your overall demand. So if you've got a system where those they're controlled like that, they have a lower demand than if they're just 15 amp circuits that are powered all the time, right? Restricted car receptacles, that's, you might see them, I know they have them out at the plant at Joffrey. I can't remember seeing any other ones. In the actual pedestal itself, there's a little 7 amp breaker, just a push button breaker. So you plug in, and if you draw over 7 amps, it pops your circuit off, right? That makes sure that people are only using their block heater instead of running a block heater and a cab heater and a battery blanket, blah blah blah, right? You can add lots of different things to a car to get her to start when she's 30 below. But sometimes you'll restrict your receptacles to keep that demand down. So make sure you have a read through Rule 8400 and see how those different types of plugs are treated in terms of demand. I did put this slide on Blackboard in course content, reading material. I can't remember what it's named, but if you look through there, you'll see this slideshow is there. So if you want to go back and have a look at it later, you're welcome to. Already went through this. Still in there, blah blah blah. And again, when we do, the main feeder in an apartment, we break it down because the chances of everybody using all the electricity available in their individual apartment all at the same time is pretty slim. So the more and more apartments you have, the less those apartments actually contribute to your main demand. Because if you got a 100-suite apartment building, because everybody lives on their own kind of schedule, right? Some people are done work at 4, some are done at 6, some work night shifts. There's people circulating in and out all the time. You don't need as much electrical demand as if everybody was on the same schedule. So the bigger they are, the less those, the more apartments there is, the less they actually contribute to your main service. So I guess the best thing to do is we're gonna just do a rundown here, and we'll do the actual calculation for this apartment. So we've got 15 suites that have a demand of 20 kilowatts each. We got 25 suites that each have a demand of 16 kilowatts. All of the smaller units, the 16 kilowatt units these units have a 2 kilowatt air conditioner. The bigger units, which obviously are the ones with the higher demand, each have a 3 kilowatt air conditioner in them. We have 60 controlled parking plugs, and in a separate laundry or a community laundry facility, or maybe there's 2 of them, we have 10 electric dryers that each rated 6.5 kilowatts, 10 washing machines at 1,500 watts. The lighting for the area, so the apartment lighting, parking lot lighting, outside building lighting, etc. Totals 12 kilowatts. And then within the mechanical room, there's 12 kilowatts of load, right? And I didn't break it down. That could be things like heat pumps, big air handling fans, whatever the case may be. Just kind of broke it down as all that kind of stuff that kind of shared to everybody. There's 12 kilowatts of it. So we're going to go to Rule 8202. One deals with how we came up with that 20 and 16 kilowatts. Number 2 is just says that it's not a continuous load. So we're going to start in 8202 sub-rule 3. So, excluding heat and air conditioning, the load shall be considered to be 100% of the load in the heaviest or the largest unit, 65% of the sum of the calculated loads in the next 2 units, 40% in the next 2, 25 in the next 15. So we got 15 suites with a demand of 20 kilowatts. In those suites is a 3 kilowatt air conditioning unit. So we actually have 15 suites with a demand of 17 kilowatts. And we have 25 suites that have a demand of 16 minus 2 is 14 kilowatts. Have a watch in the wording. Some of your questions that you're going to run into are listed this way, and in some of them it says in addition to the calculated demand shown. There's air conditioning, so just watch for those. On this one, the air conditioning units were already calculated in, and that's how we came up with 20 and 16 kilowatts. So we have to take them out because they're always going to be at 100%. So the way we do this is we've got 25s, 240s, 15 25s, 10% of the rest. Okay, so our calculation will look like this. So 100% of the largest suite, which is going to be one of these ones that has a 17 kilowatt demand. 65% of the next two largest, so we had a total of 15 here, so take 2 times 17 times 0.65, 40% of the next two, 2 times 17 times 0.4, and then 25% of the next 15. Well, we've allowed for 5. There was 15 in total, so that's 10 left over. Times the 17 kilowatts times 25%. To make this group of 15, we're going to need 5 out of this batch, or this group. So 5 times 14 kilowatts times 25%, and then everything else is at 10%. So there's still 20 of the weeks left over, so 20 times 14 times 0.1. So when you total that all up, what's that give us? So that's still all right if I move that over there, Jasper? Got less glare, but with no angle, it doesn't all show up.
Oh, how did you get again the 17 and 14 kilowatts? On the 17 and 14 kilowatts.
He removed the
So-
AC from the,
Yeah, because it says we got 2 kilowatt air conditioner units in here and 3 kilowatt air conditioner units in here. You have to take that out because we don't want to have that air conditioning at a demand of percent.
Yes.
Right? We want to allow for the full air conditioning load. Kind of chances are, you think about it, chances are when it's hot, all those air conditioners are going to be running, right? And they generally, you don't just turn an air conditioner on when you're at home. Most often you set it to a point and leave it on, right? Because it is something that the recovery time can be an issue.
so I got
And people are lazy.
140.7 kilowatts.
140.7 kilowatts. Does everybody agree with that?
Yes. Same.
Okay, so that's our suite demand, we'll call it. I guess. So that's 2023A Articles 1 through 5. B, if electric space heating is used, the sum of all the space heating loads as determined in accordance with section 62 shall be added to the load determined in accordance with item A, subject to rule 106 subrule 4. Do we have electric heating? No. Don't have to worry about that. C, if air conditioning is used, air conditioning load shall be loaded with a demand factor of 100%. Added on to A and B, subject to 8106. That 8106, remember, was the interlock rule, right? So if we'd had electric heating and electric air conditioning and they were interlocked together, just take the largest of the two. It's not the case because we don't even have electric heating. So our air conditioning load AC load is 15 times 3 plus 25 times 2 right, so we got 45 kilowatts plus 50 kilowatts, should be 95 kilowatts, right? Any electrical, so now we're on to D, any electrical vehicle supply equipment loads not located in the dwelling units shall be added with a demand factor as specified in table 38. We don't have electrical vehicle chargers, we have controlled parking lot plugs, so D doesn't apply. In addition, any lighting, heating, and power loads not located in the dwelling unit shall be added with a demand factor of 75%. So basically everything we haven't counted up, which is our parking lot plugs, dryers, wash machines, lighting, and the mechanical room load. We take all that, add it all together, and apply a demand factor of 75%. So our controlled parking lot plugs, there's step 1. We go to rule 8400. I've got to make a change in here. That 15 and 20 amp demand is new. Oh.
Yeah. That's gonna be impressive that way.
Let's just do. I'll just reopen it and edit. It's this one. Go ahead and give a shot at calculating them as if they're 15 amp. 60. 15 amp control parking lot plugs. So if we got 15 amp controlled parking lot plugs, there's 60 of them. We go to rule 8400. Not so So that we're gonna be working in sub-rule 4. So if we're on a 15 amp circuit, the first 30 have a demand of 650 watts apiece, and the next 30 have a demand of 550 watts apiece. So our parking plugs, $30 times 0.65 and 30 times 0.55, because everything else is in kilowatts, we might as well just put them in kilowatts as well, right? Make sure you do that, because if you add watts and kilowatts together at face value, it doesn't work very good. Be amazed how many times that actually happens.
36.
So the total is 36 kilowatts. Okay, so parking. Um, 6.5 kilowatt electric dryers. If they were in the dwelling unit, we'd have added them in at, 6,000 watts for the first 6 kilowatts, and then 25% for that 0.5. But these are not in the dwelling units. These are just in a community laundry facility. So there's a good chance with 40 suites in an apartment building and 10 dryers and 10 wash machines, they're probably going to get used fairly regularly, right? That's a lot of people to be doing laundry in 10 machines. So because of that, we just add them up at face value. It's simple enough. Dryers is going to be 65 kilowatts. Washers. This is a commercial setting now. We're treated as a commercial setting, not a house. When we did house panels or houses, single dwellings, apartments, whatever, a 1,500 watt load we didn't care about. It was only anything over 1,500 watts. Now that we're in a commercial setting, again, that full demand has to be accounted for. So that's going to be 15 watts, right? 15 kilowatts, yeah. 15,000 watts, 15 kilowatts. 10 times 1,500. General lighting and mechanical room load, they're given to us as 12 and 12. Add all those up.
Yeah, they add up to 140.
140. So that's our house demand, and then it says we can take the total of that and add it at 75% towards our main service. Keep this number written down because it's going to be important here in a minute. So 140 times 70% is going to be
75%. Yeah.
yes, 75%.
105.
So our total demand for this apartment building, 140.7 plus 25 plus 105, 270.7.
We're at 340.7. Or no, that sounds 200.
For
Never mind. 105. Oh,
For-
AC meant 25. I had 95.
yeah,
in
it's
AC.
90. It should be 95. AC demand.
Why didn't anybody say that earlier?
I had it written down, I didn't notice it.
It's
Whatever
95.
2 times 15 is 30, plus 3 times 25,
45.
or 3 times, it was 95, not 25.
Yeah, so with 95, then you're 340.7.
Jeez, you'd think this was my first time.
We're watching you.
I did that to test you. You guys all failed because nobody said anything. Yeah, okay. So we're 340.7 kilowatts. That's our apartment demand for the whole bill. So now that we know that, we can size out our main service and our distribution. So this is kind of more along the lines of what you'll be doing for assignment 2. Okay, so we know our main service is 12208, it's a 3-phase service. So we got 340 kilowatts of demand. So we're going to divide that by 208 times root 3. Now I'm going to need to put this.
So, yeah, 945.7 amps.
946 amps.
Yeah.
Everybody good? Everybody agree? So that means our main service, 946 amps, so we're going to put 1,000 amp fuses in here, right?
What was remember what the rule is, or like where the rule is for, like standard disconnects or whatever it is?
Table 13 gives you standard fuses, and your standard disconnect size, you just got to write down, remember,
Oh,
30, 60, 100, 200, 400, 800. 8, 12, 16, 2,000, 3,000, 4,000. So it's going to be you're going to have 1,000 amp fuses, and this will be a 1,200 amp rated switch. Pretty sure it's goes up by 400s after 8. Check. 1,000 amp fuses. We need 946 amps of conductor ampacity coming in. So what should we do? We're probably going to run some parallel runs, right? Getting fairly substantial there. Big conductors. So to save some money, let's use aluminum R90 conductors. Let's say all our termination temperature, we can spec that all equipment must have a termination temperature of 75 degrees Celsius or higher. Right, just put that in your spec for your design, and you'll be fine. Okay, so using R90 aluminum conductors, what's our best option to get 946 46 amps worth of ampacity. At 75 degrees. Any opinions, thoughts?
That'd be 15 units.
So you have to use,
You'd have to use at least 1250s, but I think you have to do the D rating.
do you want to use 1250s? That was pretty big. Why don't we just split it in three? We take our 946 and split it in three, and that gives us, 316 amps apiece, right? So we could do 3 runs of 600s. Good for 340 amps, sure. So that means we're gonna have, how many conductors in total? You saying 9?
Conductors, I think so, isn't
It's a 12208, so it's a Y service, so we need 3 hots, 3 phase conductors, and a neutral to make it work, right?
Ooh,
We
then
split that into 3 runs. So we're gonna have 3 conduits with 4 600 kc mil conductors in each conduit. Right? In each conduit, we're gonna have a red, black, blue, and white 600 kc mil conductor, and we're gonna need 3 of those to get up to the 946 amps that we needed. That making sense? Everybody good? Confused, Jasper?
yes.
Yes?
Yes.
Right, so well, somewhere.
Yeah, I can imagine how you will connect the parallel if you make a parallel.
And then this one's gonna be the same, right? We're gonna have 3 coming from here. Ah! It's a good idea at the time. Right, so we got 3, 6, 9, 12 conductors, right?
Yes.
And to make sure that they share the load evenly, and, you know, all the magnetic fields work out evenly and everything runs at its optimum, we're gonna put this one, this one, this one, and this one all in one pipe. So you got all 3 phases and a neutral in that pipe, and then we're gonna do the same 2 more times.
Okay.
So we'll have 3 conduits, each will have 4 conductors in it, and that's how that main service will be built. Does that make sense?
Yes.
Good? Okay. So for 4 600 kc mil conductors, what size of conduit do we need? We go to table 6A, because we're using R90 or RW90, whatever, they're the same size.
600,
So for
41.
600s,
Oh, no. 78.
no,
91.
we need 91.
Yes.
Minimum of 91. Let's write this one better. 391 conduits, each with 4 600 kc mel R90 aluminum conductors. Okay. That's our main service. Size, everything's good. Here, we're gonna start at the bottom and work our way up, just because frickin' string is driving me nuts. Our house panel. We calculated out our demand on that house panel of 140, we'll multiply by 75 to get 105 kilowatts, right? I told you to remember this number. The reason being is that this conductor right here, going from our distribution up to the house panel, right? It's going to go through a splitter, fuse, disconnect, and all that kind of stuff. I just broke this down to kind of bare bones for simplicity. These conductors right here have to be able to carry the full 140 kilowatts, right? Not the 105. Reason being, well, if people are downstairs doing laundry, they're probably not cooking. So, you know, if the house panel loads are being utilized to the max, there's probably some individual suites who are using less than we've allowed. So at point D right here on this map, we're going to have to size these conductors for 140 kilowatts. 140 divided by 208 times root 3, because you would run this as a three-phase. This would be a three-phase panel. So 140 divided by 360,
389.
389. So this is going to have a minimum of 389 amps. Okay.
Sorry.
So for 389 amps, let's use aluminum conductors just because I lost a bunch of money betting on Green Bay last weekend, so I got to use cheaper conductors. For 389 amps, what do we need at 75 degrees? Is it 750s or do you have to go up to 800s? 800s? Could be a little bit big. The other thing you could do is run parallels.
3. Number 3.
So you take your 389 divided by 2, and that's 250s. 195 amps. What size of aluminum conductors?
350s.
Or parallel runs at 250. So try to stay under, usually try to stay 750 or less. So I'd probably opt for the parallel 250s.
If you run parallel conductors, like say, I don't know, like say like if you did parallel conductors on that feed to the host panel, do the parallel conductors like rejoin at the panel, or like how do you?
Oh, absolutely. Yeah,
Yeah,
absolutely.
So like, is there just like a special connector you use for that? Like a Just like trying to visualize like what that would look like when it all comes back together.
There's a couple different ways it can be done. You could just have a bus bar that you mount three lugs, good for whatever, for 600 or bigger on a common bus, and then you run out and then you do the same thing at the other end. Sometimes you'll have lugs that are rated to put multiple conductors under. They have to be rated for it. You can't just take a lug that's good for 750 and say, oh, well, two 250s will fit in there and tighten her down. That's not okay. And generally, a lug that's rated for multiple conductors, when you look at it from the end, so there's a screw that comes, or a set screw that comes in the top. Usually it's an Allen key, has an Allen wrench, and then it screws down, and then the whole is kind of like this. So it's wider at the bottom and then a smaller one on top, so you put your two conductors in, tighten your lug down. Or you could use side by sides. They actually, where they make a block that has provisions for 6 conductors on them. Sometimes there's 3 doubles. There are all kinds of different configurations. But yeah, you just make sure that you've got some way of connecting them. I got another slideshow I can show to you. It's got that. So that's our house panel, and again, it's all, whether you use the 800s or the 250s, the other thing you consider is if this house panel, so if you come out of the splitter to your disconnect and then the house panel's right next to it, well, 4 feet of 800s to put in there, not a big deal, right? It's okay. If you come out to your disconnect and the house panel is quite a ways away, might be easier to run two parallel conduits and pull the wire twice rather than run them great big fellas, right? So again, all of this design stuff, there's more than one way to do it, and as you get more experience and you get doing it more and more, you'll kind of get the feel for when it's better to choose path A, path B. Right? These are just your options. Now, if it's separated out like this, so we've got one feeder that's going to go out and feed all the large suites, and another one that's going to feed all the small suites. Let's say the large suites are the top 3 floors of the building, and then the smaller ones are the next 4 floors to the building. We put one central distribution for each. There's lots of ways it could be laid out. When you come out of your main service and then you're doing feeders for a number of suites, you have to go back and you go through that same process we used to calculate our main suite demand, right? Because this is your main feeder, these are suite feeders, right? So in this case, can I get rid of all this drawing crap that I've got everywhere?
So most apartment buildings like have their own transformer of some kind, like pull down some high voltage.
Quite often there'll be this one at a 1,000 amp 208 service. Yeah, it would be done like this.
No, they just have, yeah, like you hook up to the.
You get over 1,000 amps on a 208 208 service, you might wanna bring in a 600 volt service and then put individual transformers. Depending on the layout of the building, could make a difference too, right? Because if it's a fairly spread out facility, you might bring in have a 600 volt service and then put transformers spread out around the building, so you get less line loss. Again, all depends. I've done fairly big installations with 208 volt services and just did them this way. Part of the Bauer Mall, it's a 600 volt service, and every shop has its own transformer,
No, I heard it.
right? So there's a 600 to 208 transformer in every one of them little stores within the mall.
Oh, wait.
Just because there's so much distribution that keep the voltage up, keep the current down, smaller conductors, less line loss, on and on you go, right?
Yeah, that's crazy.
Again, once you got it into watts, and you know how to calculate what the demand is, if you decide to use 600 and use a transformer because it's cheaper or better, you're fine to do that. Anyway, okay, so if all those large suites are fed out of one conduit, they were 20 kilowatt suites with 3 kilowatt air conditioners. So there was 15. So feeder, let's call it feeder B, is 15. What did I say? 20 kilowatt units with 3 kilowatt AC units in them. So again, we have to take the AC out. We're going to go right back through 82023. We're going to take the AC out, so that means we've got one 17 kilowatt times 100%, two 17 kilowatt times 0.65, two 17 kilowatts times 0.4, 10 17 kilowatts times 0.25 plus 15 times 3 for the air conditioning. That's what that calculation looked like, right? First unit at 100%, the next two at 65%, next two at 40%, the next 15 at 25%. We've only got 10. And then the air conditioners loaded, added back in at 100%.
$122.7.
122.7. Divided by 208 times root 3 gives us an ampacity of
341.
341. Okay.
This will end up, yeah, like if you added like the A and B panels there, like they'll add up to more than we calculated for our suite demand in the first place, right? Because, yeah.
So for 341 amps at 75 degrees, no, we should be 750s, right? I think 700s are quite good. If I can. 700s. So we need 700 KC mil conductors. There's going to be 4 of them. You can go to table 6 and find the conduit size. You guys are capable of that, I'm sure. So I'll go back and do, just to finish it out, feeder C, which is now 25, 50, 60? Or is that 50? 25 at 16. 16 kilowatt units that had 2 kilowatt air conditioners. So now we're going to have 14. That's 5. We're going to be 15. 14s. So 15 that's 20. And 5, 14 kilowatt units times 0.1, and then 25 times 2 kilowatt air conditioners. $152.9. By 208 times root 3, give us capacity how much?
424.4. I don't know, 425. Yeah. Okay, that's it.
So we're probably going to be splitting that in half and run parallels, right? So for 213 amps, we have to go up to 300s.
Yeah.
300 kc times 2 parallels. So this is going to have 4 conductors. We're going to have 2 conduits with 4 conductors in each here, and if, depending on how we do it, 1 conduit with 4 800 kc mils, or 2 conduits each with 4 250 kc mils at this location.
It should be parallel three wires.
Pardon me?
3 wires, because 425 amps is 900 kcml. And then if you parallel over 3,
You take your 425 divided by 2, gives you 213.
yes, I was mistaken again.
You took your size in half,
Yes,
or
yes,
you
yes.
figured out your big conductor and then cut it in half. Yeah, yeah. No, make sure. Good. No, that's good.
Yes.
So, like, as you were saying earlier, right? When you add up the ampacity, all these conductors, we got 341 plus 425 plus 389. So you're 390. 730, 1150 amps here on these conductors, but you only got 940 coming in, right? And that's perfectly fine. And it works out because, again, right? not everybody's gonna be home all the time, so, but if all the swanky folks up on the top floor happen to be home, and you've got to allow for it to distribute out, but it's still gonna be, the chances of everybody using everything all at the same time is diminishing. So we can allow for that. There's basically Labs Island too. Kind of. See, a lot of people make the mistake here that when they size that house panel, they just size this conduit and everything based on our calculated value times the 75%. And that's not okay, right? This only contributes 105 amps towards this total, but coming from the distribution out to the house panel itself, it's got that, those conductors have to be able to handle that full calculated demand. Hopefully you can see all the conductor sizes and whatnot. There, this is a close-up calculation of feeder C. Kilowatts, which ended up there. How you feeling about those?
Nothing too crazy.
Sweet.
For the purposes of this class, you know, like choosing between parallels and
Everybody's done with this, right?
yeah.
I'm gonna shut that glaring thing off.
But yeah, just for like the purposes here, like, is there like a right and wrong between like picking parallels or not or whatever? Or
Again,
aluminum, copper, like would you get that?
I usually specify whether I want aluminum or copper conductors. Really, when you get anything bigger than number 3 copper, anything over 100 amps, quite often aluminum is the way to go because it becomes so much cheaper. That's just kind of a rule of thumb. If you spec copper instead of aluminum, if it fits, you get marks for it. And I might put a comment that because it would be cheaper, you should use aluminum. But you don't get deducted for it. If it's a multiple choice type of thing, it'll tell you to use aluminum. It'll say this size of aluminum conductor or this size of copper conductor or whatever, right? So yeah, I can't be totally nitpicky about it because there's so many different ways that work, right? So put in what you want. You got a justification for it. Put a note. This is why I went this way. If it all makes sense and meets code, you're fine. Right?
Are we gonna
Do
talk
not
about- spec
spec rigid steel conduit in your apartment buildings. It's way too much money and way too much work.
Is there anything in this class about like DC
What?
stuff? Like, is there anything about DC that we'll touch on? Like
That's the way of the dinosaurs.
dinosaurs? Does DC's go along with the dinosaurs? I think DC might be the future in some cases. Like that high voltage DC stuff.
There's a lot of benefit of using DC for distribution because you get reduced skin effect in your conductors, reduced line loss, lead induction crap, that stuff that
Yeah.
happens. Yeah, distribution and stuff, DC is great. And the reason it's kind of coming back is electronic devices are so much better and cheaper than they used to be, right?
Like the solid state like switchgear.
Yeah, like, well, the reason they went from because everything started out in DC, right? That was Edison's thing. We're gonna use DC for everything. That's the greatest thing ever. But he found out, well, how do you deal with this line loss thing? Because if you want to have 240 volts in everybody's house, then that means that generating station can only put out 240 volts, and by the time you get it from there to there, those guys are only getting 200 volts. If you bump up your voltage at your generating station, the guys that are close to the generating station are getting 280. This is terrible. So they went with AC because you can transform it, change it up and down, and all that stuff. And you know that's why AC won out the war for voltage, your common delivery voltage, right? But now you can transmit in DC and put an electronic inverter and build whatever AC voltage you want, and it works just fine, right? That was because that was the big kicker was, you know, dealing with line loss and making multiple voltages available and all that kind of stuff. The only way that we used to be able to do it efficiently, cost effectively and efficiently was with transformers. But now electronic devices are so much better.
Yeah, well, and yeah, so like there's a couple of big solar projects happening in Alberta, and so like the big solar guys, like they'll be generating everything in DC already.
Yeah.
I wonder if those will hook in via like high voltage DC or if they'll.
Generally speaking, because the grid's AC, they take the solar,
And just invert it.
generate power at DC, invert it, and tie it down.
Yeah,
From one test or whatever, one of the questions is calculate the minimum capacity for each conductor with a maximum load of 600 amps. And non-linear loads account for 50
Where'd you see this?
amps. I think it's one of the quizzes or whatever.
Is there one? Did I miss that?
But my question is, the rule says non-linear load supplied from a three-phase four-wire system, you don't count,
You don't reduce.
you don't reduce, sorry, yeah. And it says, except as required otherwise by MA, demand factor 70% should be applied for everything above 200 amps. So, do you take like 550 amps and then multiply by 70%, or like, is there some kind of, like, how do you derate that?
I left this out. This is kind of a neat thing. I left it out of this course because it's cumbersome. You are allowed to reduce the size of a neutral conductor.
Yeah.
Okay? So when you go through, where is neutral conductors covered? Which code rule is that?
This rule is 4018.
4018. Okay. So it says you can reduce the neutral conductor. So coming into that building, we had an ampacity of 946 amps. Okay? So our line conductors have to be good for 946 amps. That's fine. If we wanted to, we could actually pull smaller neutral conductors because it's a three-phase system. Most of the load, if you guys have somewhere else to go ahead. This is beyond, but I'll show you just because it got brought up. The load on your neutral is going to be quite a bit less, right? If everything was perfectly balanced, the load on those neutral conductors would be zero. So why are we pulling 1,000 amps worth of neutral conductor when it's going to have 200 amps on it or something, right? So you're allowed to reduce the size of the neutral. And when you go through 4-018, it says you can reduce reduce the size of neutral, anything over 200 amps. So the first thing you do with that 946 is you take out 200 amps. So that gives us 746. You also can't reduce the neutral for nonlinear loads, which is anything that's electronic. Electronic switching loads, ballasted lighting. VFD is a terrible example because it doesn't use a neutral, but
like anything with like a weird power factor?
yeah, because you get those circulating neutral currents or harmonics and all that kind of crap builds up on the neutral. So if you have nonlinear loads, which is basically anything that's electronic, could send harmonics back into the system, you can't reduce for that. So if in that building we determined that 150 amps of the load was nonlinear, so there's a big VFD running the air handling unit, and we've got high intensity discharge lighting outside and all that kind of stuff. Calculates for 150 amps of that service. We can't delete or reduce any of that. So we have to take this out. So that's going to give us 596. Neutrals can be reduced to 70%. So we take 596 times 0.7. 596 times 0.7 equals
417.
417. And then we add back in these things we took out because we had to run them at 100%. So now 417 plus 150 is 567.
Yeah, do we add that 200 again too?
Yes, you add these things that you took out because you're not allowed to reduce them back into that. This number comes up, should be 767, right?
Yeah.
So we went from, we would actually pull 946 amp phase conductors and 767 amp neutral conductors to that service.
Save a couple of bucks, eh?
Yeah.
Especially the long run, I guess.
The conduit's a little less full. I mean, if you're pulling 80-foot long runs of 750 aluminum, I don't know what the cost of that. Those conductors each are quite a bit of money, right? So if you can reduce by $300-400, good deal. If you're pulling 80 feet of conductor, I'd rather pull 3 750s and 1 400 KC mill than pull 4 750s, right? I mean, it's just that much less weight to deal with and whatnot. It's going to make things easier, save a little bit of money. This is probably the least utilized rule in the code book, to be honest. I don't think I've done a job
I've never seen it.
where the main service reduced neutral, and a lot of them it easily could be. But I don't know why it's not used more. In fourth year in the trade, we talk on it briefly, but we don't do a lot of it because it's just for some reason not done. I don't understand why. But anyway, it's the way it works. I'm sorry if that showed up on one of the quizzes. I thought I got all of it there. Don't
Good.
you run into it, don't sweat it because